So, hi everyone. So it's 3:05 p.m. already. So since no one has joined, but I think we should start. So today we'll be going to discuss questions related to week 10 lectures. So as you can see, no one has joined the meeting. So I'll be going to each question slowly. Since I won't be having any feedback from the live audience, so I'll try to explain each and every step. And in fact, some of the questions I would repeat if I feel I have gone fast, because right now I don't have any feedback, but I'll try to be as slow as possible and try to explain each and every step, and if I feel, I'll repeat again. Also, those people who are watching the live recordings on the YouTube, in case of any doubts, they can ask in the comment section, or they can join the next session that is on the next Sunday, and they can ask in their doubts. So without further ado, I think we should start. So let me just use the introduction. We are bound to give it every time. So good afternoon everyone. My name is Musab Rafiq. I'm a PhD student in the Department of Electrical Engineering at IIT Kanpur. Today we are going to discuss the problems related to the week 10 lectures of the course Digital Electronic Circuits, that is taught by Professor Gautam Saha from IIT Kharagpur. So this is 9th April 2023, and next session is going to be on 16th April. So last week we discussed questions related to counters, ripple counters, synchronous counters, counter design using flip-flops. This week, as already highlighted here, we are going to discuss questions related to design of synchronous sequential circuit using Mealy model and Moore model. Some questions related to state transition diagrams. Few questions related to ASM chart. ASM is algorithm state machine chart. And some questions related to state transition techniques, like we have partition technique and implementation table. And using those techniques, we will see how we can reduce the number of states. So let me just start. So has anyone joined? Let me just check. No one has joined. Towards the end of the course, the live audience goes down, but let's hope you guys watch it on YouTube. So here we have a first question. This is a true or false true or false type of statement type of question. So this question states that which of the following statements are true. So we are given with the 4 statements, and we need to find out which of these statements are true. So the first statement states that the outputs are synchronized with the clock for both Mealy and Moore models. Number 2, in a Moore model, the input only affects the internal state and not the output. Number 3, in a Mealy model, the input affects both the outputs and the internal state. And number 4, the Moore model is more sensitive to glitches in the input as compared to the Mealy model. So let's just go through each statements one by one. So we have the statements: the output are synchronized with the clock for both Mealy and Moore models. So this statement is wrong. Outputs are synchronized only for Moore model. In Mealy model, outputs are not synchronized as they are dependent on the input and the internal states also. So if there is a change in the input, the output will change. It is not synchronized with the clock. So this thing is incorrect statement. Next, in a Moore model, the input affects only the internal state and not the output. This statement is correct, because the Moore model, you know that it affects only the internal state of the model machine, and then in turn that affects the output state. So only input affects only the internal states. So this statement is correct. So number 2 is correct. In a Mealy model, the input affects both the outputs and the internal states, as I earlier said it when I was discussing the statement 1. This statement is also correct. In a Mealy model, the input affects both the outputs and the internal state. And now the final statement that we have here is, so this was also correct. So 2 and 3 are correct. Now the final statement is, the Moore model is more sensitive to glitches in the input as compared to the Mealy model. This is wrong, because Moore model output is dependent on the internal state and not on the inputs. In melee, it's dependent on the inputs and as well as the internal state. So in the glitches in the input will directly affect the output in case of the melee model, not in the mole model. So this should be converse. The statement as it is wrong. So statement number 2 is correct and statement number 3 is true. So let's just check which of the options has 2 and 3 is the option. So A has 1 and 3 only, B has 2 and 3 only, C has 1 and 4 only, D has all of the above. So 2 and 3 are correct, so option B is our right answer. So the output are synchronized for melee Moore model only, and the melee model is more sensitive to glitches in the input as compared to the Moore model. So this was the correct answer, and the correct answer is option B. Let me just check whether someone has joined. No one has joined. So let's move forward to question number 2 of today's live session. So question number 2 states that the following state diagram is a dash model, whether a melee model or a Moore model, and it corresponds to dash sequence detector. So we need to find out the sequence it detects, and we need to figure out whether it's a melee or a Moore machine. So the state corresponds to the follows. You can write the state diagram. Let me just put this here. Yeah, it's fine. Corresponds to the follows. So state A, we are starting at state A. No bit is decoded at here. No bit is decoded correctly. So this can be said as the initial state. IS stands for the initial states. So as I don't have space here, I'll use the acronym for that. Now I'm going to B. When I'm going to B, so when we are looking for these sequence detectors, always look for the forward propagating arrows. So we have this transition from A to B when 1 is an input. So 1 bit is dictated and the sequence detected so far is 1. Now I'm at state B and I'm looking at the forward propagating arrow. So this one goes to this thing, to C, and 2 bits are decoded, and the sequence that is detected is 1 1. Now I'm at D, so I'm making this transition. So 3 bits are detected, are decoded correctly, and the sequence that is detected is 1 1 1. Now at state E, when 0 is here, 4 bits are decoded, and the sequence that is detected is 1 1 1 0. Now at F, 5 bits are detected, and the sequence that it is detected is 1 1 1 0 and then 1. So from state E, when I have input 1, I go to the state F with output as 1. So that means when output goes to 1, my sequence has been detected. So in all other cases you can see the output was 0. Only when this sequence was formed 1 1 1 0 1, the output changed to 1. So the sequence that was detected was 1 1 1 0 1, and as you can see the inputs only change the state, and only when it reaches a particular state then only the output changes to 1. So this is a Moore machine. So 1 1 1 0 1, so option B is the correct answer, and this is a Moore machine. So what we have this initial state A, where this bit was which was initially initial state. Then I went to B on the input pattern of 1, then went to C on input pattern of 1, then so on up to I went to E on input pattern of 1 1 1 0, and when I hit another one I went to state F with the sequence that was detected was 1 1 1 0 1. The sequence that was detected was found out by the change of output to 1. So this was question number 2. Now we'll move forward to question number 3 of today's live session. So let me just put it here. So question number 3 states that consider the state transition diagram given below. So we are given the state transition diagram. If only D flip-flops are used for realization of digital circuit, so only D flip-flops are used for the realization of digital circuit, then which of the followings are true? So among the 4 options we need to find out the correct digital realization of the following state diagrams, and given is the X is the input, Y is the output, and B and A are the states of flip-flops D, A and DB, DB and DA respectively. So we are given the state diagram, and then we are given this, what should I say, we need to find out the digital realization. So let's just first construct, so let me just put it here. Let's first construct a state table, then we can proceed. The state table can be made up like this. So here I'll just write state table, and here I'll write PS, that stands for present state. So how many states are there? 1 2 3 4 A, B, C, D. States here are 4 states, namely A, B, C, D. And my next state is dependent on the input, and the input can be X equal to 0 and X equal to 1, and based on the input I can move to the next state. And also we have outputs. So outputs are X equal to 0 for X equal to 0, and for X equal to 1. Now I'm here. Let me just close this one also. So when I am state A, my present state is state A, and my input is X equal to 0, I'll just remain at A. Just look at the state transition diagram. I'm at A for input 0, I'll just remain at A, and my output is 0. When I'm at B, my input is 0, I'll just go back to A, and my output is 0. When I am at C, I'll receive as 0, I go to D with output as 0. And when I am at D, I go to A for input equal 0, X equal to 0, and my output is 1, as you can see here. Now when I'm in state A and my input is 1, I go to state B with output equal to 0. When I'm at state B, I go to state C for input X equal to 1, and my output is 0. When I'm at state C for input X equal to 1, I stay at C, and my output is 0. And when I'm at state D and my input is 1, I go back to state B, and my output is 0. So this is my state table. Now how many states are there? there are 4 states A, B, C, D. So how many flip-flops are required? It's given in question 2 flip-flops, but let's just show how 2 flip-flops are required. So I have 4 states, right? And the number of flip-flops that are required to represent these states is given by ceiling function of what? Ceiling function of log 2 the number of states that I will represent by S. Just wait a second. Okay, sorry about that. So number of flip-flops is equal to ceiling function of log 2 states. So it can be written as ceiling of log 2 of 4, that is ceiling of 2. So I'll just write CE for ceiling of 2, and ceiling of 2 is simply 2. So 2 flip-flops are required, and as was given in question, that is DB and DA. Now using 2 flip-flops we can represent states as, so states are represented as by this B, A. So we can represent A as, so here is B, here is A, where B is the output of flip-flop DB and A is output of flip-flop DA, A, B, C, D. So these can be represented as 0, 0, 0, 1, 1, 0, 1, 1, right? So let me just draw another table. So here I will have it's better to create a table, that's better. So let me just insert a table. So how much I need, so let me just draw it. It will just take time. So here I'll just write input. So this is my input, that is X, so it can be 0, 0, 0, 0, 1, 1, 1, 1. Then I write present state. So present state can be represented by B and A. So present states are 0, 0, that corresponds to A, 0, 1, that corresponds to B, 1, 0, that corresponds to C, and 1, 1, that corresponds to D. Here I can also write in brackets A, B, C, and D. Then again I will write here 0, 0, 0, 1, 1, 0, and 1, 1. So here it's A, here it's B, here it's C, and here is T, right? Then I have next state that corresponds to here, that I will write B plus and A plus. So when I am at state A and my input is 0, where do I go? I just remain at A. When I am at state B and my input is 0, where do I go? I go to A. When I am at state C and my input is 0, where do I go? I go to D, so 1, 1. And when I am at D, my input is 0, I go back to A, so it's 0, 0. Similarly, we can fill it here. So when for A input is equal to 1, I go to B, that is 0, 1. When input is 1, I am at B, I go to C, that is 1, 0. When input is 1, I am at C, I go to remain at C, so that is 1, 0. And when I am at D, my input is 1, I go to B, that is 0, 1, right? Then here we will have outputs, that is Y, and this thing is 1 only for when I am at D and my input is 0. When I am at D, my input is 0. For other cases it's 0, 0, 0, 0. So 0, 0, 0, and then 0, 0, 0, 0, right? So this is the table I constructed, and you know the excitation table of a D flip-flop is somewhat like this: Q plus Q, 0, 0, 0, 1, 1, 0, 1, 1. So here is D is simply equal to 0 0 1 1. It's equal to Q plus. D is simply equal to Q plus. So here this was Y. Now I need to write dA and dB and dA, since we are following that notation. So it's dB and dA. So B plus is 0, so this will follow directly here, 0 0 1 0 1 1 0. Based on this equation, D is equal to Q plus, and this thing will go here, 0 0 1 0 1 0 0 1. So here B plus and here dB is equal to B plus, and here, so you can just look at the excitation of table of D flip-flop, and from there I am writing these things. So A plus, so I'll just write here 0 0 1 0 0 0 1. Now I'll just draw the K map for dB. So I'll just draw a K map for dB. Here I'll write X. Here I'll write B and A. So this thing is 1 thrice. It's 1 here, here, here. This is 0, this is 1, this is 0 0, this is 0 1 1 1 0. So this forms a pair, and this is as it is. So dB is simply equal to, from this I get BA complement plus this term, this is X B complement A. Similarly for dA, I'll just make a K map, and I'll just mark all the ones, so no pair is formed. So dA is simply equal to all three even terms, XB complement A complement plus XB A plus X complement B A complement, and output Y is 1 only for this thing. Output Y is simply equal to, output Y is equal to BA X complement BA. So Y is equal to X complement BA, dB is equal to BA complement plus XB complement A, and dA is equal to XB complement A complement plus XBA plus X complement BA complement. So option D is the right answer. Option D is the right answer. So here what I have written, here I have written inputs, here I have written states, where A is marked as 0 0, B is marked as 0 1, C is marked as 1 0, and D is marked as 1 1. Here I have written next states based on the state transition diagram and looking at the state table. Then I have written these transitions, and then I have written dA and dB and dA based on the excitation table. And for D flip-flop, you simply write dA is equal to QA plus and dB is equal to QB plus. That is here B plus and A plus represent QB plus and QA plus, and here is the output Y based on the state table. And finally I wrote these three equations from the K map, and this Y is simply this min term, and I will just mark option D as my correct answer. Now moving forward to question number 4. So question number 4 has, consider the following state table. So we are given this state table where we have these states S0 to S6, that are 7 states, and then we have next states based on the input combination, and then we have the output based on the inputs. So we need to find the equivalence classes obtained using the row elimination method, and we need to figure out, based on the equivalence between the rows, we need to find out the equivalence classes. So let's just see a table here and just look at it. So first let's see which of the table match to one another, where the outputs and the states are equal. So here S0, let's just check S0 and S1. So S0 S2, so let's just omit it. Let's just check S0 S2, so S0 S0 S1 S1, let's just leave. S0 S3, so S0 S3, these are different. Then S0 S4, this is also different, as outputs are different, I can simply neglect it. Then S0 S5, output different. S0 S6. So looking at these things carefully, we find that S4, let's just look at S4, the outputs 0 1 0 1 are equal, and the states S0 S5 and S0 S5 based on the input combination are same. So S0 and S5. Wait, someone has joined in. So we are discussing question number 4 for today's live session, and the question states that we need to reduce the following state table using the row elimination method and find the equivalence classes. So based on that, we find that S0 and S4 and S6 are same. As you can see, equivalent S0 S0 S5 S5 and output is same. So we can just write S4. We can just write S4 for S4 S6. We can just write S4. So here I have written this S4 S5 for S4 S6 for S4 for only S4 S6. As S4 is equal to S6, wherever there was S6, we just replace it by S4. So S5 was S6 S5. So I'll just replace it by S4, and here S4 as it is, and S5 S5. And as you can see, now S3 and S5 are equivalent. See, S4 and S4 are equal, S5 and S5 are equal, and outputs are also equal. So here, from here, we got S4 and S6 are equivalent, and from here in the next step we've got S3 and S5 are equivalent. So no further equivalency is possible. So my final table will look somewhat like this. So wherever there is S5, I'll just separate it with S3, and wherever there is S6, I'll just separate it with S4. So my final table is somewhat like this, and my equivalent classes are S0, S1, S2, then there is S3, S5, that is one class, and then there is S4, S6. So we have S0, S1, S2, S3, S5, S4, S6. So option D is my correct answer. So someone had joined, but the person left. No issues. We can move forward to question number. What was this? This was question number 4. Now we can move forward to question number 5. So the question number 5 states, the states of a state transition diagram are given as. So the states of a state transition diagram are given as 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and 1, 0, 0. Now the question asks us, find the number of flip-flops required in the digital circuit realization of the state transition diagram. So we have this state transition diagram that has some number of states, and we need to find out how many flip-flops, minimum number, are required to implement it digitally. So we need to find out the number of flip-flops required for the digital circuit realization of the state transition diagram having these states. So as you saw earlier in, I think, question number 2, or which one was it? As you saw earlier in question number 3, yeah. As you saw earlier in question number 3, we saw number of flip-flops. So let me just write completely. Number of flip-flops required are equal to the ceiling of log 2 of what? Log 2 of number of states. So this ceiling function, so you guys might be knowing this ceiling function, this gives us the integer greater than the integer. Means if I have to find out the ceiling of 2.5, so I need to find out the greatest integer above, that is first, the greatest integer that comes first after 2.5, that is my ceiling function. If it's 2.5, my ceiling of 2.5 is 3. If it's ceiling of 2.1, my ceiling of 2.1 is 3. If it's ceiling of 4.4, it's 5. If it's ceiling of 7.6, it's 8, like that. So I need to find out the this log2 of number of states. Now let's just count the number of states given here. These are 1, 2, 3, 4, 5, 6, 7, 8, 9. So number of states here are 9. So the ceiling, so the number of flip-flops required will be equal to the ceiling of log 2 of 9. So what is log 2 of 9? So its ceiling of log 2 of 9 is 3.17, and ceiling of 3.17 is, we need to find out the greatest integer that first comes after the number. So 3.17, the greatest integer that immediately comes after 3.17 is 4. So 4 flip-flops are required for this implementation of this state transition diagram, where the states are these. So option 4 is my correct answer. Let me check whether someone has joined. No. So let's move forward to question number 6. Consider a Moore machine with 3 flip-flops, 1 input and 1 output. So we have a Moore machine with 3 flip-flops, 1 input and 1 output. So we need to determine the number of transition arrows leaving and the number of transition arrows entering a state. So we need to determine the maximum number of transition arrows that are leaving a state and the maximum number of transition arrows that are entering a state. So for maximum number of transition arrows leaving a state are simply equal to number of maximum. So I should write max here. Maximum number of transition arrows leaving a state is simply equal to 2 raised power number of inputs. So how many inputs are there? 1. So 2 raised power 1. So that is 2. Now we need to find out the maximum number of transition arrows entering a state. So that is equal to maximum number of states, maximum states that are possible, multiplied by maximum number of arrows leaving a state. How many states are there? So how many maximum states are there? So this can be found out. States can be found out simply by 2 raised power number of flip-flop, and this is equal to 2 raised power 3. Since number of flip-flops given are 3, so this is equal to 8. So maximum states that are possible are 8, and the maximum number of arrows leaving a state we just found out was 2. So the maximum number of arrows entering a state is equal to 16. You can simply say that there are 8 states, including the state itself. So what is happening? For both the inputs, first the state is going back to its own state, and from all other states, for all other input combinations, that is coming to this state. So that's why it's 16 arrows coming to this state, and 2 maximum number of arrows that are leaving are based on, because what will be the number of arrows leaving? It will be the number of maximum number of arrows leaving will be the maximum number of inputs. So that are 2. Since input is only 1, it can be either 0 or 1. So there are 2 possible arrows that are leaving and 16 possible arrows that are coming. So option B, 2, 16 is my correct answer. So let's just take it's 3:39. Let's just take a 2 minutes break here. So to those guys who are watching the recording on the YouTube, they can move forward by 2 minutes. I'll just resume after 2 minutes. Thank you. So let's just resume. So far we have discussed 6 questions. Now we will discuss question number 7. So let me just put the camera here first. So question number 7 states that given the state diagram in the following figure, so we are given the state diagram, determine the equivalence classes obtained using implication charts method. So based on the implication charts method, we need to find out the equivalence classes. So equivalence classes can be found out using the implication charts method. So let's just proceed. First we will construct the implication table. First we'll construct the state table. So here I have my present state, right? Here I have my next state, and here put is x equal to 0 and x equal to 1, and this is like this. Then I have my output, present output, for x equal to 0 and x equal to 1. So this is A, this is B, this is C, this is D, and this is E, and we have F also here. Now at state A, when I get input 0, I remain at state A and my output is 0. When I'm at state B, my input is 0, I go to state C and my output is 0. When I am at state C, my input is 0, I go to E and with my output equal to 0. When I am at state D, my input is 0, I go to state B with the output as 0. When I am at state E, my input is 0, I go to state C and my output is 0. And finally when I am at state F, my input is 0, I go back to state B and my output is 0, right? Now looking for the input combinations of 1. So when I'm at state A, my input is 1, I go to state B with output as 0. When I'm at state B, my input is 1, I go to state D with output as 0. When I'm at state C, my input is 1, I go to state F with output as 1. When I am at state D, where is D? Yeah, D, and my input is 1, I go to state A with output as 1. When I am at state E, my input is 1, I go to state D with output as 0. And when I am at state F, my input is 1, I go to state A and my output is 1. So this is my state table. Now we will construct a implication chart. So what we'll do, can we construct it here? Yeah, I think we can. So let's just construct an implication chart. So here I will write A, B, C, D, E, and from here I will write B, C, D, E, F. So now let's just look at B and A. So B and A is one the same thing. So their outputs are same. So first we'll mark the crosses for all those boxes where the output is different. So A and B is same output, A and C are different outputs, so A and C have different output. Let's just mark cross. A and D have different output. Let's just mark cross. A and E have different outputs. Let's just mark. A and E have same outputs. Now let's A and F, they have different outputs. Let's just mark them cross. Right. Now C and B, they have different outputs. Let's just mark cross. C and D same output. C and E different outputs. No, C and E should be having same outputs. and E. When I'm at C, I have 0, 0, 1 and E, 0, 1 and now E, E 0 and D 0. Okay, so I have to check. I'm checking D and B. I should check D and B. Sorry, D and B. D and B outputs are different. So mark D and E, they have same outputs. Then D and B and F, they have different outputs. Mark. Then C and D have same outputs. Let's keep it as it is. C and E have different outputs. Mark cross. C and F have same outputs. Then E and D have different outputs marked with cross, and then E has different outputs with F marked with cross. Now we have to look at A and B. So they have the same outputs. When will be the equivalent? When A is equal to C. Let me just mark it with different color. So A and C and B and D, they should be equivalent. When is E and F equivalent? When C is equal to B, equivalent to B, and A is equivalent to D. So A and E needs to be checked. A and E, A equal to C and B equal to D. A equal to C, A equal to C, B equal to D, equal A, C, B, D. Yes. Now I need to check E and B. A and B. So when C is equal to C, that's simply the same, and D equal to D. So I'll just mark 2 ticks here, they are equivalent. Now I'll just check D and C. D and C will be equal to when B is equal to E is equal to B and A equal to F. For F and C, E equal to B, A equal to F. For F and D, B equal to B, A equal to A. So this is right here. Now let's just evaluate this condition. Now I'll just use another ink color. Now let's just check this condition. So A equivalent should be C, and as you can see, A is not equivalent to C, so we'll mark it as cross. And here A is also not equal to C, so we'll mark it as cross. Now E equivalent should be B. E should be equivalent to B. E should be equivalent to B, and A should be equivalent to F. As you can see, A is not equivalent to F. We will mark it as cross, and we'll mark it as cross. So what we'll have here? So we'll have E, we'll get E. From D is equivalent to F, so we can write DF, and here we have E. From C we have nothing, so we'll write C, then E, then DF. Then from B is equivalent to E, so we can write B, C, we can write BE, DF. And finally from A we'll have A, so finally we'll get A, C, BE and DF. These are my final equivalence classes obtained after the implication task method. So what I'm doing here, I'm just checking. So here no is equivalent, so I'll just write E. Here D is equivalent to F, so I have written as DF. Here no class is equivalent, so I'll just written C. So here B is equivalent to E, so I have written as BE. So B is equivalent to E, so I'll just put them in one class, BE. Here no class is equivalent, so I'll just put it A. So A, C, BE, DF. So A, C, BE, DF. So option B is my correct answer. So has someone joined in? So no one joined in. Now let's move forward to question number 8 of today's live session. So deduce the type of flip-flop from the following ASM chart. So from the following ASM chart, we have to deduce the following ASM flip-flop. So just looking at it clearly, so when I'm at input, output is Q equal to 1, and I am getting A equal to 0, and if my B is equal to 0, I'll just remain at 1. If my B is equal to 1, I'll just go to Q equal to 0. So you can see that 0, 1 output just goes to 0, and for 0, 0 it just remains as 0. So from that you can deduce it's somewhat related to SR and JK flip-flop. So we can just write here JK flip-flop table, where J is equal to A and K is equal to B. So I can just write the characteristic table of JK flip-flop here. 0 0 0 0 0 1 0 1 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So when my both inputs of JK flip-flop is 0, my Q plus is simply equal to Q. So it's 0 1. When my input to JK flip-flop is 0 1, my output will be 0. When my input to JK flip-flop is 1 0, my output will be 1 1. And here for 1 1, toggling will happen. That is Q plus will be equal to Q complement. So it is 1 0. So as you can see, this chart is showing the valid operations of a JK flip-flop. As you can see, when my Q is equal to 1 and my A equal to 0, so A is equal to 0 and B is equal to 0, I am at 1, right? And when B is equal to 0, I'll go to 0. So this here. And when Q is equal to 0, A is equal to B is equal to 0 and A is equal to 1, I'll just go at 1, and when B is equal to 0, I'll just remain at 0. Where is it? So when Q is equal to 0, so Q is equal to 0 here, and my B is equal to 0. So Q is equal to 0, B is equal to 0 will be this, and Q is equal to 0, it will remain as 0. So it's following the valid operation of JK flip-flop. Also, this thing is following the valid operations of a SR flip-flop. How? Let me just construct a SR flip-flop characteristics table here. And here, input A is equal to S and input B is equal to R. And here it's my Q, and here it's Q plus. So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. For 0 0 0, output will just remain at Q. 0 1, it will be 0 0. 1 0, it will be 1 1. And here it are don't care. These are invalid conditions. And as you can see, the chart follows the valid operations of SR flip-flop and also the valid operations of JK flip-flop up to here. So JK and SR, for conditions apart from 1 1, they have the same characteristics table. If you can see, they have the same characteristics table apart from the conditions when A is equal to 1, B is equal to 1. So that thing never occurs here in this ASM chart. So we can say that the type of flip-flop that this chart is following is JK flip-flop or SR flip-flop. So option C is the correct option. Now question number 9. Just a second. Question number 9 asks us to perform the state minimization of the given state table using the partitioning method. So earlier we saw this row table method, then we saw the implement chart method. Now we need to find out the minimization using the partitioning method. So here the state table is given. Here the next state is given for the input combination 0 and 1, and here the present output is given for the input combination 0 and 1. So here I'll just construct a table, partitioning table. Here I will just write the partition number, that is P, and here I will just write down the states. So first partition, we'll just write the things as it is. So A, and here we'll just write the outputs for x equal to 0 and x equal to 1. So the outputs are 0 0, B, C, D, E, F. Outputs are 0 0, B is also 0 0 for input combination 0 and 1. Then it's 0 1, then it's 0 1, then it's 0 1, and then it's 0 1. So we need to partition based on the states that have the same output. So as you can see, A and B, they have the same output, and C, D, E, F, they have the same output. So I'll just write A, B, C, D, E, F. So the partition would be somewhat like this. Now I have to write the next states based on the input x equal to 0 and x equal to 1. So x equal to 0 and x equal to 1. So A has states A, B has states C, D, C has states E, F, D has states B, E has states C, D, F has states B, A. So the next partition will be, so the partition now is based on that the states should be in the same block. So if you can check the A and B, these states are A and B, A and C, so they are in different blocks. So A is in this block and C is in different blocks, so that means they need to be separated. So this is A, it will be A and B, this will be B, this will be C and D, so this is one block. Now for this block, let's just check first the four states together. So E, B, C, F. So E, C, F are in one block, but B is in another block, so therefore can't be grouped together. Now just check C, D, E. So E, B, C, again B is in this block and E, C is in this block, so C, D, E. So the next possible grouping can be C, D. So E, B, E is in this block and B is in this block, so not possible. Now let's just check F, E, C, not possible. So also no combination of three blocks possible. Now just check two blocks. So C, D we have already checked. Now we will just check C and D. So C and D, so states are E, C that are in this block, F, D that are in this block. Now C and F, E, F, so E and F are in this block, but F and A is in this block. So with C only E will go. So that is E and F and C and D. What about D and F? So B and B that is in this block and A and A that is also in this block. So D and F will also be grouped together in the same block. So we have these blocks. After that no further splitting is possible, because after that this is already separated, and this you can see E is in different block and C is in different block. EC are in the same block, FD are in this block, and BB are in the same block, and A are in the same block. So no further splitting is possible. So my equivalent states will be A, B, CE and DF. So what are my states? Those I have blocked together. So DF, CE, B and A. DF, CE, B and A. Option C is my right answer. So far we have just solved 9 questions. Let's just wait for another 2-3 minutes. Let's just take a short break for 2-3 minutes. Those who are watching the live recordings, most of you will be watching the live recordings, they can seek 2-3 minutes forward and just check it. Question number 10. So welcome back. So now let's discuss question number question number 9 we'll discuss. Now let's just discuss question number 10. So the question number 10 states that a sequence detector is designed to detect precisely 3 digital inputs. So we have a state sequence detector that is designed to detect 3 digital inputs with overlapping sequences. So overlapping sequences will be also detected. Let's just say I need to detect 10. Let us say I need to detect 001 or 101 as in the case. So if I get a pattern like 10, if I get a pattern like 1101, so it will detect the last 3 bits as 101 as the input detected. So the second bit it kind of overlapped and we will get the sequence. So the question asks us, a sequence detector is designed to detect precisely 3 digital inputs with overlapping sequence detectable for the sequence 101. So 101 needs to be detected and the input data 110, 100, 110, 10110. What is the output of this detector? So you must be aware of that a sequence detector gives us the output 1 whenever a sequence is detected, whether it be in case of overlapping, whether a sequence, whenever a sequence is detected, 1 will be output, and in case of non-overlapping, when a sequence is detected, output will be 1. So what I have here is I have an input and I have a sequence 101. So this is the sequence that is detected. It will give the output 1. So first output will only be there when 3 bits are given as the inputs. Till then, no having output will be of no there will be no output. So the first output will only be there when first 3 bits are detected. So because 3 bits are detected precisely, here you can see number of inputs are 14 and number of outputs are 12. So first 2 bits only when the third bit is given, the sequencer will give me the outputs. So my first 3 input are 1, 1, 0. So 1, 1, 0. So when 1, 1, 0 is given to this input sequence detector, what will be my output? My output will be 0 because 101 needs to be detected. Now this bit is discarded in my MSB. My next 2 bits 1, 0 and my incoming input, that is this one 1 is there. So first we will have these 3, then we will have these 3 and so on. 101. So what is 101? The sequence that needs to be detected. And what will be the output? The output will be 1. So then it's 0, 1 and my next input is 0. So what will be my output? Output will be 0 since 101 needs to be detected. So what's my next input? 1, 0, 0. So that's also not the case. Now what is my next input? 0, 0, 0. This is 1, 0, 0, 1. So 0. What will be the next output? 0, 1, 1. So again 0. I'll just write others here. So 0, 1, 1. What will be my next output? 1, 1. What will be my next output? 1, 1. So far I am here is 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 1, 1. Then it's 1, 1, 0 and my output is 0. Then it's 1, 0, 1 because of this one, so output will be 1. Then it's 0, 1, 1. Then it's 0, 1, 0 because of this, so output will be 0. Then it's 1, 0, 1 because of this, so it will be output 1. Then it's 0, 1, 1, so output will be 0. And then it's finally 1, 1, 0, output will be 0. So my output with sequence is 0, 1, 0, 0, 0, 1, 2, 3, 4, 5 zeros, then 1, then 0, then 1, then 0, 0. So 0, 1, 0, 1. So the among these 3, then 5 zeros, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So among option 2 and 3, then it's 1, 0, 1, 1, 0, 1, then 0, 0. So option 2. 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0. So option 2 is my correct answer. So what we did here, we just took first 3 bits as inputs and just check that whether that one check the output. so that was not the correct sequence. Then the next input came, since we are looking at the overlapping detector, since it's given, let's say overlapping sequence will also be detected, so this one is discarded, then it's 101, then this one is 010, then it's 100, and so on, and we have the output equal to 1 whenever 101 is as the input stream. Now this question is solved. We can go to question number 11. So the question number 11 asks us, the state diagram for a finite state machine with states A, B, C and binary inputs X, Y and Z is shown in the figure. So we have state transition diagram shown in the figure. We need to find out which of the following statement is correct. So given here is there will be some state that is ambiguously defined, and we need to find out which states is that ambiguously defined. If there is no state, then we will mark option 4 as all the transitions are defined unambiguously. So let's just construct the state table. So I can just write from state diagram. So here are my inputs X, Y and Z, and here are my states: present state, next state, PS, NS, then finally PS, NS. Why I made these columns? This for state A, this for state B and this for state C. So input combinations can be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Then I have 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So for 3 inputs, these are the all input possible input combinations. So here I will have A. My present state, I'll just write A for all. My present state is A, 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 A. So when my X equal to 0, Y equal to 0 and Z equals to 0, I will go to B from A. When my X equal to 0, so X equal to 0, Z equal to 1, I'll just remain at A. I don't care about what will be the value of Y. So when X equal to 0 and Z equal to 1, I'll just remain at A. Now when X equal to 0, and Y equal to 1, when X equal to 0 and Y equal to 1, so Y equal to 1, whatever be X and Y, Z, I don't care, so I'll just remain at A. When X equal to, this was 1, 2, 3, when X equal to 0, Y equal to 1, and so Y equal to 1, we got Y equal to 1, I don't care about any other condition, so I'll just remain at A. Now when X equal to 1, Y equal to 0 and Z equal to 0. So for, you can see X equal to 1 and Y equal to 0, I don't care about Z, I'll just go to C. When X equal to 1, Y equal to 0, Z equal to 1, again 1, 0, I'll just go to C. Now X equal to 1 and Y equal to 1. X equal to 1 and Y equal to 1. So I get a Y equal to 1. So for Y equal to 1, I don't care about the X and Z. So I'll just remain at A. And I'll just remain at A. So you can see all the states are well defined. So there is no ambiguity in state A, transition in state A. Now let's just check transitions in state B. So when X equal to 0 and Y equal to 0 and Z equal to 0, so X equal to 0, Y equal to 0 and Z equal to 0, so Y equal to 0, Z equal to 0, I don't care about X, so I'll just go back to A. So Y equal to 0, Z equal to 1, Y equal to 0, Z equal to 1, I'll just go to C. X equal to 0, Y equal to 1 and Z equal to 0, Y equal to 1, I don't care about any other inputs, so I'll just remain at B. Then X equal to 1, Y equal to 0 and Z equal to 0, I'll just go to A. Y equal to 1, I'll just remain at B. Then Y equal to 1, Y equal to 1, Y equal to 1 and Z equal to 1, I'll just go to C. X equal to 1, Y equal to 1, Z equal to 0. X equal to 1, Y equal to 1, I'll just remain at B. this should be C. X equal to 1, y equal to 0, z equal to 1. This should be C. This is C. So for all transitions of state C, state B, they are also well defined. Now let's just check C. When x equal to 0, y equal to 0 and z equal to 0, it will just remain at C based on this condition. Z equal to 0, I hit a z equal to 0, I'll just remain at C. When x equal to 0, y equal to 0 and z equal to 1. So here I have condition y equal to 1, z equal to 1. So y needs to be 1. So here I have condition x equal to 1, z equal to 1, and here I have z equal to 0. So this is not specified. Then x equal to 0 and y x equal to 0, z equal to 0, I'll just remain at C. And x equal to 0, y equal to x equal to 0, y equal to 1, x equal to 0, y equal to 1, and z equal to 1. So I'll just go back to B. Now x equal to 1 and y equal to 0, x equal to 1, y is equal to 0, x is equal to 1, y equal to 0, and z equal to 0. I'll just remain at C because z equal to 0 means I have to remain at C based on this condition. Now 1, 2, 3, 4, 5, so 1, 0, 1. Now x equal to 1 and y equal to 0 and z equal to 1. X equal to 1, y equal to 0 and z equal to 1 means x equal to 1 and z equal to 1 are satisfied. I'll go to A. Then finally x equal to 1 and y equal to 1 and z equal to 0. Z equal to 0 means I am every time remaining at C. So you can see alternately C, 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 C. Now finally I am having x equal to 1, y equal to 1 and z equal to 1. So here z equal to 0 is not satisfied. Here I equal to y equal to 1 and z equal to 1. And here I have also, you just see x equal to 1, y equal to 1, y equal to 1 and z equal to 1. Z equal to 1 has transitions going to A and z equal to 1 has transition going to B. So z equal to 1 has transition going to A and z equal to transition going to B. And also x is equal to 1 is satisfied here and y is equal to 1 satisfied here. So this condition is satisfied by these two, this condition is satisfied by these two. So all of the three are not there in one condition, so we don't know where to go and there is a ambiguity. Here this was not specified, here we have ambiguity based on this condition because x equal to 1, z equal to 1, we have x equal to 1 and z equal to 1, it is going to A, and y equal to 1, z equal to 1, it will be going to B. So we don't know where to go. So here we have ambiguity. So the transitions from state C are ambiguously defined. Now to question number 12. The question number 12 is another theoretical question. So question number 12 asks us, the statement which is not applicable to a Moore machine, number 1, output is a function of present state only. Number 2, it requires a more number of states for implementing. Kindly read it as sum in place of same. This is sum. Input changes does not affect the output. And finally, the characteristic equation output zt can be given as zt is equal to g of s of t x of t, where s of t is the state and x of t indicates the input. So you must be well aware of that. Output of a Moore machine only depends on the state. So this one is correct. This is true. Then it requires more number of states for implementing sum of function, as you have seen in the lectures. So for some of the function is required complexity is more. So this is also true. Input change does not affect the output. This we saw only present of function of present state only. So input change only depends. So input change does not affect the output. So this is also true. Now option 4, the characteristic equation of z dot t can be given as this, where it is dependent on input, but the output of the Moore machine is not dependent on the input. It's only dependent on the internal state. So this is false. So the correct answer to this question is, since we need to find out which one is not applicable, we need to find out which one of the statement is false. So option 4 is the correct answer. Now over to question number 13. The number of flip-flops, JK flip-flops, required to design a mode type sequence detector to detect input sequence 1010 is. So we need to detect a input sequence 1010 based on a mode type sequence detector, and we need to find out how many flip-flops are required to achieve that. So number of states, first we need to find out the number of states. So the number of states are in a Moore machine is simple E equal to number of bits to be detected plus 1. So how many bits are to be detected? That's 4, and 4 plus 1 is 5. So number of states are 5. Now we need to find out how many flip-flops are required to implement this sequence detector. So we saw it earlier also. The number of flip-flops is simply equal to ceiling of log 2 of number of states, and that thing is equal to ceiling of log 2 of 5. Log 2 of 5 is 2.32, and we need to find the ceiling of 2.32, that is greatest integer that comes first after the number, that is 3. The ceiling function is only applied to the fractional part. For integer itself, the ceiling is itself the integer is itself the ceiling. So ceiling of 2.32 is 3. So option 3. So here the options are given according to the number itself. So option 3 is the right answer. Now we have a question here. For the circuit shown in the following figure, representation of state diagram is, so we have a D flip-flop whose output Q is connected to the input of the mux X1, and output Q bar is connected to the input of the mux X0, and we have a select line A, and we have output Y. We need to find out the state transition diagram based on this. So you might be aware of this D flip-flop as we have done earlier. We have this equation Q of n plus 1 is equal to simply equal to D, right? And here Y is equal to D is equal to A bar X0 plus A bar A X1. So D is equal to A bar X0 is Q bar, A bar Q bar, and A X1 is Q. So D is equal to Qn plus 1. So Qn plus 1 is equal to A bar Q bar plus A Q. So what is this function? So this is simply an XNOR function. So Qn plus 1 is equal to A XNOR with Qn. Now we draw a table here, and we have A and we have Qn. So possible input combination are 0 0 0 1 1 0 1 1. My next state will be equal to Qn plus 1. So 0 0 is 1, 0 1 is 0, 0 0 is 0, 0 1 1 is 1. So how I have written it? Based on the function A Qn plus 1 is equal to A XNOR Qn, and we know that the output of XNOR is high when the both inputs are equal. So here the states are Q equal to 0 and Q equal to 1, right? So when Q equal to 0, I am making a transition to Q equal to 1 when A equal to 0, right? So you can construct the state diagram from this table. When Q equal to 1, I am making a transition to Qn plus 1 equal to 0 when A is equal to 0. When Qn is equal to 0, I am remaining at 0 when A is equal to 1. Q equal to 1 will remain at Q equal to 1 when A is equal to 1. So the transition are being made only for A equal to 0, and the state remains at the same state when A equal to 1. So option A1 is the correct answer. So if you remember, I think in week last was week 9, in week 8. In week 8 we had a similar question, but that time we had taken a different approach to solve it. This time we have taken a more thorough approach to solve it. So you can just refer this one. It will clear all the doubts. Since that time some people have doubt, but I had cleared that doubt in the session itself. But this time I have taken a different approach to solve it. So this is one elaborative method to solve it, and I hope there are no doubts. In case there are, please type in the comments, or you can ask me next time. Better to ask me in person. and I hope I can clear those doubts. Now we have this question number 15. Question number 15, what it reads as, I'm not able to see it. Let me just see it on the screen. Okay. From the given circuit, so we have this circuit. From the given circuit, the correct values of A, B, C and D in the following state diagram are. So we need to fill out the values of A, B, C and D, and each state in the above diagram is represented as BA. So BA, that are the outputs of flip-flops, represents the states. So what we have here, let's just see what is SA equal to. So this is an SR flip-flop, huh? So SA is equal to simply A complement, if you can look at this, and RA is equal to what is this equal to? I'm not able to find what is RA is equal to A complement. This thing, this, hey, RA is equal to A. RA is equal to A. Now let's just check SB. SB is equal to B complement A. So I can write A B complement, and SRB is equal to RB is equal to A and B, AB, right? Now let's just draw the truth table here. Let's just draw truth table here. We have initial condition. We have SA, we don't know about it. We have RA. Let's just assume QA is equal to A. QA is simply A equal to 0. We have SP, RB, then we have B, and we have X. And let's just assume B is equal to X. So this is the initial condition. Now the first state, and SA will be equal to A complement. So A is equal to 0, this will be 1, and RA is equal to A, so it will be 0. And we know that when S is equal to 1 and S is equal to 1 and R is equal to 0, output will be 0. SB will be equal to AB complement. A is 0, B complement is 1, so it will be 0. AB is also 0, so it will be 0 only. And the output X, so X also, we need to write the equation of X also. X is equal to A dot B. X is equal to A dot B, yes. X is equal to A dot B. A dot B. And RB is also equal to A dot B. RB is also equal to A dot B. RB is also equal to A dot B, yeah. Now the next state, SA will be equal to A complement, so it will be 0. RA will be equal to A, so it will be 1. This is 1. This is 1, and this will be 0. SB will be equal to A B complement. A is 1 and B complement is 1, so it will be 1, and this will be 0. This will be 1. So output here was 0. Output here is AB. A is equal to 0, B is equal to 0, it will also be 0. Now state C, 3. A, so I write 1, 0, and output will be 1. SB, so SB here I will write SB is equal to AB complement. AB complement, so A is equal to 0, B complement is equal to 0, so it will be 0, and this will be 1. This will be 0 also. AB, A is equal to 0 and B is equal to 1, so 0, so this will be as it is, so it will be 1, and my output will be 1. AB is equal to 1. Now 4, SA is equal to A complement is 0, RA is equal to 0, the state terminal is 1. SB is equal to AB complement, A is equal to 1, B complement is equal to 0, it will be 0. RA is equal to AB, so it will be 1, it will be 0, and it will be 1. So my states are presented as BA. So this is B and this is A, this is B and this is A. So I'm starting at 0 0, I'm then going to 0 1, then I'm going to, so I'm at 0 0, I'm going to 0 1, so 0 1, then I'm going to 1 0, then I'm going to 1 1, and then I'm going to 0 0. So this was 1. How I found this was error was here, because you can see SA and RA, they are always complement of each other. That's why I was able to figure out this error. So the shades are going from 0 0 0 1 to 1 0 to 1 1 to 0 0, right? And when I'm moving from 1 when I'm moving from 1 1, when I'm moving from 1 0 to 1 1, the output goes to 1. So based on this, I can just say D is, so D is, when I'm going to 1 1, my output is 1. So D is 1 1, and D is going to 0 0. This is going to 0 1, and this is going to 1 0. So A is equal to 0 0, B is equal to 0 1, C is equal to 1 0, and D is equal to 1 1. So option 3 is the correct answer. So how I was able to write this D equal to 1 1? So see, when I'm here, so my B is 1 and A is 0, I am at 1 0. And when I am going to 1 1, that is B equal to 1 and D equal to 0, my output changes to 1. So C would be 1 0 and D will be 1 1, because output is 1 only here and no other cases here, and rest are simply filled up by the transition. So from 1 0 I go to 1 1, and 1 1 to 0 0, all other are built. So option 3 is the correct answer. Now over to the last question of today's lecture. It says that a finite state machine with one input x and one input z is defined by the state diagram below. Assume that the finite state starts in state A, and given the following sequence of input x values, what state is the FSM at the end of the above sequence? What input sequence is detected by the FSM? So we need to find out, based on the input sequence, in what state I am in based on the input sequence, and what is the sequence detected by the FSM. So let's just look at here this, and first try to find out. I am at state A. When I am getting 1, I am going to state B, and when I am getting to B, I am going to state C. When I am getting 0, I am going to state C, and when I am getting 1, I am going to state B, and with the output 1. So output will be 1 when 1 0 1 is detected. So this thing is pretty straightforward. So this is a 1 0 1 sequence detector. Now we need to find out in what state I am. So I am initially at state A, right? What is my input? 1. So when input is 1, I am going to state B, right? When input is at B, I am getting 0. Where I am going to C, right? At C, I am getting at C 1 0 1 0 0 1 1 1 0. Oh, so I am getting 1 0, yeah, 1 0 0. Yeah, so see what is happening. At A I'm getting 1, I'm going to B. At B I'm getting 0, I'm going to C. And at C I'm getting 0, I'm going back to A. Now I'm at A. 1 0 0, so I'm at here A. These three are done. Now I'm getting 1, I'm going back to B again. I'm getting 0, I'm going to C. And I'm getting 1, I'm going to B. I'm getting another 1, I'm going to B again. I'm getting 0, I'm getting to C. I'm getting 1, I'm going to B. I'm getting a 0, I'm going to C. I'm getting a 1, I'm going to B. And finally I'm getting a 0, I'm going to C. So 1 0 0 1 0 1 1. So these need to be marked here. This will create a confusion. So here I'm getting 1, then I'm getting 0, then I'm getting 0, then I'm doing 1, then I'm getting 0, then I'm getting 1, then I'm getting 1 again, then I'm getting 0, then I'm getting 1, then I'm getting 0, then I'm getting 1, then I'm getting 0. So finally I'm at a state C, and 101 is detected. So that was all for today's lecture. let's just wait for a couple of minutes and see if someone join. And to those watching the live recordings, they can close the video. Nothing else will be discussed. So we will meet next week on, that is 16th of April 2023, and it will be the week 11th live session. So it will be live session number 11th, and we'll be discussing later some DACs and ADCs related questions, and there are only 2 remaining sessions. 10 sessions have been done and only 2 sessions are remaining. So the next one will be on 16th and the final one will be on 23rd of April, where we will be discussing questions related to memories and all. So only 2 sessions are remaining, and we'll meet next week on 16th of April at 3 p.m. To those watching recordings, if you have any doubts, any queries, you can just type in the comment section of the YouTube video, or if you have time, you can just join the live session next week and ask me the doubts, so we can discuss at the end of the live session or before the start of the live session. So at start, I have this 5 to 6 minute buffer, so within that buffer you can ask me your doubts, and then if you want to leave the lecture, you can leave and you can watch the recordings again. There's no issue. So thank you for watching the video. I hope I cleared your doubts. We'll meet next week. Thank you.